we're going to take a look at the binomial theorem. The binomial theorem, which is in this box up here, can get kind of complicated. I'll show you this first, and then we're going to take apart pieces of it to try to understand the whole thing. But the binomial theorem says if we have a binomial that we're trying to raise to a power, this is how we can do it without using methods like FOILing or distributing or box method. The first item in that binomial is going to be x to the nth. Then we're going to have an n, x to the n minus 1, and then we introduce the y. This pattern is going to continue. We have this thing which we're going to talk about. The x is now n minus r, y is also r. We continue until x gets to the first power, y to the n minus 1, and finally y to the nth. Very complicated, a lot of pieces to it. Let's start with the numbers in front. This thing right here. This NCR is a combination. It's something we use in probabilities. I like to think of this C as a choose because the order doesn't matter. So N choose R, and here's the calculation. Now sometimes you'll see N choose R or NCR written in shorthand like this. It means the same thing. It's the same calculation. The nice thing about this, most graphing calculators, Desmos, has this function built in. You don't have to do this calculation, but this is how it's done. So let's take a look at a couple of examples. So if we have 8 items and we're choosing 2, according to this, we're going to have an 8 factorial, 8 minus 2 factorial, and a 2 factorial. And we're supposed to work that out. 8 factorial, 6 factorial, a lot of things cancel out. I get to divide out that 2 factorial, I get a 28. You can verify that with a graphing calculator or with Desmos. If I have 7 and I want to choose 0, 7 factorial, 7 minus 0 factorial, and a 0 factorial. Now, some people think that a 0 factorial is 0, it's actually 1. There's one way to write 0 items. So the 7 over 7, and this turns out to be 1, because that 0 is not a 0. 0 factorial is actually 1. And I did a couple that are written in this other form as well. Same calculation, 10 factorial, 7 factorial, 3 factorial. This turns out to be 120. 8 factorial, 8 minus 8, that's 0 factorial, with another 8 factorial, this turns out to be 1. The reason I start with those numbers is that N choose R is how we get the coefficients for our binomial expansion. So these numbers that are in front all have something to do with that N choose R. Now, the cool thing about those numbers, yes, you can do this calculation, but there is another method we can use to come up with that, and that's based off of Pascal's triangle. If you haven't seen Pascal's triangle before, there's a lot of patterns in here, but the way it's built is we always add the 2 that are above to get the next one. So I took these 2 and added them to get 3. Those got me 3, and the 1 and the 0 that's not here gave me the 1. The 3 and the 1 give me 4, 3 and 3 give me 6. So it's always built on the 2 that are above it. The other way that Pascal's triangle is built is using this concept right here. Now, we need to make sure we're naming this correctly. This is technically row 0 of Pascal's triangle. This is technically row 1. This is technically row 2. And you'll notice in row 2 there are 3 things. In row 4 there are 5 things. So it's always one more. So if they ask me to come up with row 5, I should have 6 items. I'm adding the 2 that are above. And I can generate Pascal's triangle. The other way that we can generate Pascal's triangle is using this concept right here. Now, if I take that row I just found, the way I find this item is I take 5, because I'm in row 5, and I choose 0 items. You do 5, choose 0, you're going to get 1. To get the next item, I do 5, choose 1. Then I do 5, choose 2. 5, choose 3. 5, choose 4. And 5, choose 5. And this is the key. If I would have started at 5, choose 1, I wouldn't have got that last term because I would have stopped here. So there are 6 items because we start with 5, choose 0. Again, all of these numbers, these Pascal triangle numbers, these combination numbers give us that front number. So let's practice this just a little bit. I want to find the 8th row of Pascal's triangle. So I set it up just like I did with row 5. I said 8, choose 0. 8, choose 1. 8, choose 2. 8, choose 3. 8, choose 4. And the cool thing about Pascal's triangle is it's symmetrical. You'll notice that the numbers on this side are the same as the numbers on the other side. So I've already got everything I need. I'm going to kind of work backwards. That's the 8th row of Pascal's triangle. Now, could I list this out and keep going? Sure. But sometimes I just want to jump to where I need to be. Here's the 8th row of Pascal's triangle without having to do all of Pascal's triangle. So we've looked at the coefficients. Now let's try to apply this to some examples. I'm going to start with x. Since x is first, notice that it matches the power that's here, and it's going to go down. N minus 1, n minus 2, n minus 3, n minus 4, n minus r, and I get down to where I have a first power, and then there isn't any x there. If I in turn take a look at y, but I'm going to actually go to the end, you'll notice that y starts with that same biggest power. And it goes down by 1, goes down by 2, down by 3, we get to r, we go all the way down to 1, and then this doesn't have any y's. So if I look at it in pieces, do the coefficients first, do the powers of x second, do the powers of y last, I can piece this thing together and I can do a binomial expansion. We're going to start with just an x and a y, just like the binomial theorem has, and we're going to raise this to the 4th power. Now, could I do this with FOIL, box method, things like that? Sure, I certainly could. But I'm going to try to use the binomial theorem. The binomial theorem says since we have a power of 4, I'm going to use the 4th row of Pascal's triangle for my coefficients. Those are the numbers that go in front. Now I'm going to tackle x, and it's going to start with the 4th power and go down until I don't have any x's for this last term. Now I'm going to look at the second term, and I'm going to actually start at the end, and it's going to start with a 4th power and go down as I work right to left until I don't have any for this first term. If I put in my plus signs, here is the full expansion of x plus y to the 4th power. That would be x plus y times x plus y times x plus y times x plus y. 4 of them done by using the binomial theorem. Now, some things to note. The power here is 4, the power here is 4, and you'll notice if I add the powers, they always add up to 4. You'll notice that the numbers follow Pascal's triangle. If I don't want to use Pascal's triangle, I can do 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, and 4, choose 4. I'll get the same numbers. Now, it works for x and y, it works for numbers, it works for a lot of things. So let's slip a number in here. I've got a 3rd power, so I am in the 3rd row of Pascal's triangle. That means there's going to be 4 items. 1, 3, 3, and 1. And I want to start with the first term as the cubed squared first power. This one doesn't have any. I don't have a variable for my second term, so I've got 1 cubed, 1 squared, 1 to the first, and then this doesn't have any. So I expanded it the same way. I should go back and do the numbers. I can do 1 to the first, multiply it by 3. I can do 1 squared and multiply it by 3. I should always do the numbers if I can. So in its final form, I get 1x cubed, 3x squared, 3x plus 1. There's the full binomial expansion of x plus 1 cubed. Now, the reason I do it this way is, what if this x plus 1 cubed was actually x minus 1 cubed? Doesn't change anything that I do, except what's in the parentheses here is negative. So it's going to change my signs. This is positive, but now this is actually going to be negative. This one would stay positive, but now the last one would be negative. So it helps me keep track of those negative signs as I'm expanding my binomial. Let's try one that's just a little bit harder. I'm going to go back to the fourth power, so it's going to match the same row of Pascal that I used up here. I could do 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. And I'm going to give myself plenty of room. Now I notice that my first term is a 3x. So I'm going to put that 3x to the fourth here. Notice I'm using parentheses again. My cubed term, my squared term, and my linear term. My second term in this binomial is a negative 2y. So I've got my fourth power, my cubed, my squared, and my first power. So technically, I have this expanded, but obviously it's a little complicated because there's a lot of things in here that I could do. So I'm going to go back and do what I can. 3 to the fourth I can do. It's 81. And 81 times 1 is still 81. So this is 81x to the fourth. The fourth goes to both parts. That's the first term in this expansion. A little more complicated here. I've got 3 cubed. That's 27. I've got a 4. That gives me 108. And I've got a negative 2. That gives me a negative 216. So I just did the numbers first. Now I'm going to go back and say I've got an x cubed and a y to the first power. I'm just simplifying at this point. Here I have a 3 squared, that's 9. Here I have a 2 squared, that's 4. The negative takes care of itself. So 9 times 4, that's 36. And a 36 times 6, that gives me 216 x squared, y squared. Just a coincidence that they're the same. Here I'm going to do the negative 2 cubed. That gives me a negative number, negative 8. And I'm going to take the negative 8 times the 3. That's a negative 24. And negative 24 times 4 is a negative 96. X to the first, y cubed. And my last term here is negative 2 to the fourth, that's 16, and 16 times 1 is still 16, y to the fourth. Here's the full expansion of that binomial. No FOIL, no box method, no distributing, just using the binomial theorem. Now, sometimes they will slip an extra power in there. As long as this is a binomial, so 2 parts being raised to the power, what we're doing here will still work. I still lay out my coefficients. I'm in row 3 of Pascal. I'm still going to start with my first term, x squared. being cubed, then my x squared being squared, then my x squared being to the first power, and then I don't have an x squared for that last one. Then I'm going to work backwards with my 4. I've got a 4 cubed, a 4 squared, a 4 to the first, and I don't have one for that first term, so here it is. Without multiplying it out, I should go back and actually multiply it out. Power to power, so I get an x to the 6th. Here I get a 12, x to the 4th. 4 squared is 16, so here I get a 48, x squared. And 4 cubed is my 64. There's my binomial expanded without having to do any foiling, box method, distributive property.